Hello, everyone. Welcome to the network security session. And the first presentation will be Gollector, measuring domain name dark matter from different vantage points. And Kaspar Hageman from Aalborg University, Denmark is going to present us this paper.
Okay, so thank you very much for the introduction. So my name is Kaspar Hageman, also from the Aalborg University, and I'm presenting our work on Gollector, a tool for measuring domain name dark matter. And the story of this paper and this work starts with a simple domain name, pretty much the naming convention of hosts and resources on the internet. By looking at different data sources, a single domain name actually has a rich information attached to it. So if you look at zone files and whois information on the top left, you know something about the registration, when it was registered, who owns a particular domain name, which is quite relevant for let's say malicious domain registrations. Then we have on the right we have passive DNS, which is the passive DNS, the passive collection of DNS traffic, which allows researchers to investigate and observe let's say the access patterns for a particular domain name, from what geographical locations are a domain name being requested, who is interested in visiting this domain, all the way to the the hosting part fraction of DNS. What is the IP address that hosts a particular domain? And then a third example on the bottom is certificate transparency, which is a relatively new system in which newly issued certificates, TLS certificates, are being published by the certificate authorities. By observing these certificate transparency logs, you can also infer some certificate issuance behavior for particular domain names. And the thing is that depending on what source you use and for how long you measure or collect data from a particular source, you get a different set of information to you have that to your disposal. And in our case, we refer to these different points of data collection as a vantage point. And even though they are significantly different in the amount of data that you collect, there's usually a overlap between all of them. Is that they provide a different view of the total domain name space, so the domain names that actually exist, and the timing of the observation of this. Just to give an example, if you as a researcher only look at these certificate transparency logs, you will only see domains popping up that actually use TLS or use certificates in one way or another, and thereby you will completely miss all the domains that don't use any TLS. Whereas the other side, if you try to collect, let's say, a DNS at a top level domain name server, let's say a Russian authoritative name server for the .ru domain, for instance, then you will hardly or not see any non-Russian domains. So these two vantage points give a very different view of what part of the domain space you will see. And this is exactly what we refer to as domain name dark matter, is that certain points or certain parts of the domain name space at a particular point in time are hidden or are invisible from the perspective of that vantage point. So that's what we call domain name dark matter. And this is exactly what we in our research wanted to investigate. Can we leverage the relative domain name dark matter between different vantage points for several security contexts? And in order to do so, we started coming up with we wanted to have a method that sort of collects the information from these different vantage points. So in this case, we have 3 vantage points: the zone files, the certificate transparency logs, and different types of passive DNS. Feed is in a black box that allows us to analyze and compare these vantage points easily. And the actual implementation of this black box is Gollector. Just to summarize the contributions from this work and also this presentation is that first of all, we present the design of Gollector. So what are the design choices that we made to collect all our domain name dark matter? And then show the utility of our tool by applying it to 3 different use cases. And along the way, this presentation, I will sort of dive deeper into what these use cases are. So in a nutshell, Gollector consists of this framework, or the different parts within this dotted line. So we have these different data sources on the top. So I won't go into too much detail, but there's a specific framework by ICANN that allows us to collect zone files called the, I think it's centralized zone file data service, maybe, at least CZDS. Then from our university network, we get access to a set of Splunk logs, which represent the passive DNS that we collected. There's one data set that is not shown here, which is called Entrada, which is a passive DNS data set from an authoritative name server. And then we have all these individual certificate transparency logs that we consider individual data sources. And for each data source that we have we've implemented a dedicated collector, which is a very small component that is tasked to fetch entries, or what we call, I guess, entries from these data sources and insert them into and send them to a sink. So they're pretty much only tasked to interact with these external data sources. Then we have this sink component in the middle. This sink receives all the entries from the collectors and inserts in the underlying database. Right now we use a simple Postgres database, which works fine for our use case, but the design should allow for sort of replacing this with maybe a more large-scale solution. And then, so the Postgres database maintains a set of tables that allows us for the sort of easy data analysis, post-analysis that we want to do. I try to go through this a little quickly, but for more information, please look at the paper. So we more or less maintain 2 sets of tables. On the right, we have an anonymized version, and on the left, we have an anonymized version. And what we do is that for every domain name that we see, that we observe, we create several models in the database based on the part of the domain name that we see. So for the top level domain, let's say for google.com, the top level domain is com. So we will sort of split the domain name into these different parts: the top level domain, the public suffix, the apex, the root part, and then the fully qualified domain name. And store the domain name in all of these tables with a reference to them. So by doing so, for instance, it's very easy to see, to query the database, how many fully qualified domain names for a particular apex domain have we seen, or how many fully qualified, how many top-level domains have we seen, and how many domain names have we seen across them. And then we also maintain a set of entry tables that you can see on the bottom for the different data sources, and they point to the database models that are relevant. We also maintain this anonymized version. This was because researchers may have access to only a sensitive data set that the actual owner of the data set rather not disclose the information in there. So we came up with this method to strike a balance between anonymity and still the capabilities of analyzing the data afterwards. So what we have is that this anonymized table stores the hashed value of salted hashed value of the domain name part, and only if the unanonymized version of exists, then we store a reference between them. So we can actually see that if we collect, let's say, a domain name in Entrada, and we've seen the same version pop up in a zone file entry, then we actually can relate those two domain names to each other using that reference. So that's pretty much the design of Gollector in a nutshell, the major contributions. And then we apply Gollector to 3 use cases. The first one being the early detection of domain names. Then we look at a specific setup of our university network and look at the potential data leakage that happens. And then we also look at to subdomain enumeration and our contribution to that field. yeah, so I won't go into too much detail about the data collection, but we collected 3 weeks of data from the same time span for all the different vantage points. We collected them from 4 vantage points. So the certificate transparency logs, the most of the zone files that we could get access to. There's about I think 1,100 zone files, if I remember correctly, and then 2 passive DNS data sets. One of them being our university network. So that was the all DNS requests that go towards the resolvers maintained by our university network in Aalborg, and then also the DNS traffic towards the Danish authoritative name servers. So the .dk domain, they've shared their data with us as well. And they're stored in a system called Entrada. So if there's some images or tables with Entrada, then that represents the traffic to the Danish authoritative name servers, all DK domains there. So let's go into the early detection of domain names. And the question that we posed here is the zone files that we have access to, they're only updated once a day. So the granularity or precision of data collection is quite limited. So if you as a researcher are interested in getting very timely information, then zone files may actually not be the best way to get data to get access to. So that's why you want to investigate if these non-zone file data sources or vantage points, can we leverage them for early domain registration detection? And what we wanted to do is to investigate using the zone files as a ground truth. How many domains do we identify earlier using a different vantage point than the zone file itself? And these are the results. So these tables are a bit complicated, a bit messy, I realize. But just to give an example, so for the certificate transparency data set, we found the left cell that is marked here, around 568,000 domains that were identified before the zone file saw them. And on the right side, that's the percentual representation of this number compared to our ground truth, which is from the zone files. So out of all domains all domain registrations that we've seen in the zone files, the CT logs saw 13.8% of them before the zone files did it. And we did this both for the entire data set, so for all top level domains, and the Danish domain only, because our Entrada data set is very skewed towards Danish domains only. And you can see that that's represented in this bottom right percentage over here. And there are 3 rows overall before and within 7 days, and that is represents the time limit that we set for which we included a domain name to be considered before the zone file. Again, I would recommend reading the paper because I don't have the time to explain it too thoroughly. Conclusion, at least the conclusion here is that the certificate transparency, as you can see on the upper red box, they actually, a lot of domains are actually identified before the zone file does. So they are actually, these CT logs are actually a very relevant data sets to use for early domain registration detection. And Entrada is actually really good for doing this for the Danish domain. Of course, the limitation for this Entrada data set is that we only have the access for the Danish domain. And in order to get access to all top level domains, would actually be quite a challenge for most researchers. So the certificate transparency is actually a good alternative to do so. So that was the first use case. The second use case that we looked at is, can we use Gollector and the domain name dark matter to identify some domain name information that's leaked outside our university network. So a domain name itself can potentially be sensitive information. Imagine having a domain name that has a name that's related to, let's say, an internal server service that's running there. So it actually discloses a little bit of the infrastructure of an internal network, which can be considered private in some cases. So that's why I wanted to investigate. Is there actually some data that's being leaked outside of our university network? And in order to do so, we want to—
You have 5 minutes left.
Oh, 5 minutes.
Yeah.
Okay, that should be fine. Thank you. So in this case, we use the passive DNS data from our network resolver, so the university network. And we also use the passive DNS data from our authoritative name server. That's the Danish one. So we can only compare, let's say, Danish domain names. A good thing is that if you look at this table, these are the unique fully qualified domain names and the apex domains in which they fall. And you can see that the vast majority of fully qualified domain names falls under the au.dk, which indeed is the domain name owned by our university. All the other domains are more related to some background traffic, which is not necessarily related to the university. So luckily, we can actually observe this traffic at the authoritative name server, the Danish one. And what we found is that out of these 3.8 million fully qualified domain names under au.dk, about 18,500 of these have been seen outside the university network. So they've been seen at the Danish authoritative name server. That in itself is not necessarily a problem, because many domain names are only accessible outside, let's say the publicly available website, for instance, and probably some other services as well. So that's why we went to look into both domains that have been seen inside and outside the university network, which were about 2,800. And out of those, we wanted to investigate to what extent are these actually private. So we removed the domains that are very common. So we looked at the list of the top 1 million most common subdomains, I think, and we subtracted that from the 2,800 domains. And this ended up with 2,300 non-common subdomains, which is quite alarming, actually. So there's actually 2,300 subdomains that can be seen outside the university network that are not really common. So we haven't done a more in-depth use case or case study on these subdomains, but it is kind of, it shows that some information actually leaked outside a university network. And then the last use case that we did is towards subdomain enumeration. And this research question tried to figure out if we can use our data set to find subdomains under a given apex domain without relying on usual word lists or guessing or otherwise existing methods that some penetration testing tools use. So what we came up with is a methodology where we represent our data set in a graph notation, where every node in the graph is a subdomain, and the edges between a subdomain represents the degree to which these two subdomains have been seen under the same apex domain or set of apex domains. And the weight of this edge is between 0. That means that these subdomains have never been seen under the same apex domain, or 1, which means that these subdomains are always seen under the same apex domain. Using this huge graph, we found cliques in this graph, which are subgraphs in which all nodes are connected to all other nodes. And this was based on the assumption that all these subdomains in a clique are highly related and correlated to each other, because all of them are seen at least once under the same apex domain. And then we use these cliques to generate candidate domain names, which means that we have a set of subdomains. We have a set of apex domains under which these subdomains have been seen, and which means that if you take the sort of Cartesian product between those two sets, you can find all candidate FQDNs. Some of these we already have seen, and we only look at the ones we haven't seen before. And just to give an idea of these cliques, so on the last column, you see a set of examples of subdomains inside this clique. So the first one is very high entropy subdomains, probably auto-generated. The second one are related to email protocols, IMAP, POP, SMTP, some languages, some content delivery networks as well. And we actually found that out of all the candidate FQDNs that we generate, we found that 59% of them actually exist, which is way higher than we actually expected. We expected more something in the range between 5 and 10%, which means that as a penetration tester, this can actually be quite relevant to instead of sort of brute forcing the generation of subdomains, you can actually use a method like this to find candidate FQNets. So I hope I'm still within time. We have open source Gollector. You can find it on this link here. I hope the slides will be distributed so you can find it. Yeah, again, this tool, at least the results in this tool, are mostly to illustrate utility. So we would recommend encourage the research community and all of you who are listening to see if you can use Gollector for your research. So that's it. Any questions?
You can raise your hand, and if you want to ask a question, or write it to the chat. Okay, I can ask one question. This tool, it's a good way to actually discover security vulnerabilities, and security companies are using similar tools. So what was the most interesting finding you figured out when you scanned, for instance, subdomains?
I think, well, it's one of the more interesting things that we find is that we started looking at these cliques, and there were quite some interesting ones. One interesting example that I've never been able to explain is that there are some cliques that we found under, they always appear to be under two Russian top-level domains. One is the RU, and the other one is, I think, the .su, the Soviet Union top-level domain, which should have been defunct by now, since 1991 or something about that, like that. So we actually found a lot of domains or cliques like that for which we saw a subdomain that existed both under the or an apex domain that existed both under the Russian and the Soviet Union subdomain. Unfortunately, I've never been able to figure out what these domains did, because that was not really the depth to which we went with this research. But there are definitely a lot of interesting cliques that we found, for sure.
Yeah, thank you for the presentation. It was interesting and actually very relevant from the security point of view. This is a tool that someone can actually use in real life.
Yes, it's open source available. It's very easy to get up and running with, I think it should be relatively easy to, at least it was designed to be relatively easy to add more of these collectors to it. So if there are particular vantage points that people are interested in, then it should be pretty easy to get started with, and pull requests and contributions are always welcome.
Yep, thank you. We have to actually move on. So to the next
Thank you.
presentation.